Hi everyone, my name is Noa Garcia and I'm going to introduce our paper, A Dataset and Baselines for Visual Question Answering on Art. In the last few years, there have been many different applications of computer vision for art, especially when applied to fine art paintings. Some of the most notorious applications are painting classification, object recognition in art, or style transfer. There has also been interest in exploring joint language and vision models in art. For example, by using a piece of text, being able to find the painting that it is most suitable. Following this direction, in this work, we investigate the potential applications of visual question answering in art. At first glance, visual question answering in art presents some more challenges than visual question answering in real images, as questions might not only be related to the image content, such as how many people are there or is it sunny, but also to the form or the context of the artwork, such as who is the painter. The contributions of our work are fourfold. First, we explore the topic of question answering in art, which requires not only to understand the visual content of paintings, but also to acquire related knowledge about their context. Second, we introduce a preliminary dataset for visual question answering in art, which we call AQUA. Third, we propose a baseline model, which we call VIKING, which is able to reason over the painting as well as to leverage external knowledge. And fourth, we conduct a thoughtful analysis of the challenges of visual question answering on art and its potential future directions. Let me now introduce the AQUA dataset. To create a visual question answering dataset, we rely on the SEMA dataset, which contains around 20,000 images of paintings, each of them associated with an artistic comment, description, and some metadata. We transform this data into questions and answers for the AQUA dataset using state-of-the-art visual and textual question generation techniques. More specifically, from the image of the painting, we generate visual questions using two techniques, one based on object detection and the other one based on caption generation. Also, from the comment of the painting, we generate knowledge-based questions using text-based question generation. To generate the visual questions using object detectors, we rely on two techniques. First, we use Amazon recognition to extract the objects that appear in the image. Even though Amazon recognition has been trained using real images, we have found in our experiments that it works surprisingly well in paintings. Then, we use the detected objects as possible answers, and together with the image of the painting, we generate questions using the state-of-the-art AQUA model for visual question generation. Let's now see how we generate the visual questions based on captions. In this case, we first generate captions from the paintings using Pythia and convert the caption to a question and answer pair using the rule-based question generation model by Hellman and Smith. Finally, we also convert the comments into questions and answers using the same rule-based question generation model. Differently from the visual questions, the questions generated from the comments are especially focused on the context of the painting. As the questions and the answers are all generated automatically, we perform a quality check on the data. We use Amazon Mechanical Turk and ask humans to rate each question-answer pair according to 6 metrics: grammatical correctness, answer existence and correctness, whether the painting is necessary to answer the question, whether the contextual knowledge about the painting is necessary to answer the question, and finally, the reasonability, which judges if the question-answer pair looks human-generated. We found that in general, questions are grammatically correct, and visual questions tend to need the information of the painting more than the knowledge questions, which is also true in the other way around. To ensure a good quality in the dataset, we perform a cleansing with human annotators to remove samples that have strong grammatical errors or whose answer does not exist. After this process, the dataset ended up with almost 80,000 samples, split into train, validation, and test set, with more than 30,000 samples being visual-based and more than 45,000 samples being knowledge-based. Also, by exploring the difference between visual and knowledge samples, we found that the knowledge questions tend to be much longer than the visual ones. Next, we introduced VIKING, our baseline model to address visual question answering in art. VIKING consists of three parts: a modality selector, a visual QA branch, and a knowledge QA branch. Given a painting and a question, the modality selector classifies the sample into the two different modalities so that it can go through the corresponding branch. We use a pre-trained BER model to encode the question and a ResNet to encode the painting. The samples that are predicted as visual questions are sent to the visual QA branch. We use IQN for answer prediction, trained for answering questions, which is a different model for the one used in the AQUA question generation process. Finally, questions classified as knowledge base are fed to the knowledge QA branch. We create a knowledge base with all the comments in the SEMAR dataset, and we retrieve the comment that is the most relevant to the question with a two-stage strategy. In the first stage, we apply TF-IDF to rank all the comments. The top-ranked comments are re-ranked in the second stage using BERT. The answer is predicted based on the question and the best-ranked comment with a XLNet model. We first evaluate several baselines together with our VIKING model in the AQUA dataset. Our first set of baselines are both blind and ignorant, answering questions without paintings and without external knowledge. The accuracy, which is measured as the number of exact matches, is less than 20%. The second set of baselines use paintings but not external knowledge to answer questions. We use bottom-up, top-down attention and BAN. These models perform slightly better than the ones without painting information. Finally, for our VIKING model, we have three variants: VIKING without the knowledge QA branch, VIKING without the visual QA branch, and the full model. It can be seen that the knowledge branch performs much better than the visual branch, which is consistent because there are more knowledge-based questions than visual questions in the dataset. The full model, however, is able to fuse the best of the two branches to boost accuracy up to 55%. Now we show you some of the results of the visual branch. And some of the results of the knowledge branch. Although the encouraging results in our experiments, we are aware of the limitations of our work. Visual question answering on R is still far from being solved, and the aim of this work is to serve as an introduction to the field. We discussed the limitations of both the AQUA dataset and the VIKING model. For the AQUA dataset, we found three main limitations. First, the generated questions are either visual or knowledge, but usually not both. Second, the visual questions are based on an object detector trained on natural images, which inevitably introduces noise into the dataset. And third, because the questions have been automatically generated, the diversity of the type of questions is rather limited. As for the limitations in the VIKING model, we found that first, it does not consider the differences between the artistic styles, which is a very important aspect in the visual appearance of paintings. And second, the same source of external knowledge information is used both for the question generation and the question answering. A more challenging scenario would be to use different sources of information to answer the questions. As a summary of this presentation, we would like to highlight the following ideas. We have introduced a new task for visual question answering in paintings. We have introduced a dataset for this task. We have also proposed a model as a baseline to solve the task, which outperforms a standard visual question answering model models by a large margin. However, in this work, we assume that external knowledge is strongly tied with the questions, which can be seen as an upper bound of the performance of this dataset. As future work, we will explore other sources of information, such as Wikipedia. Thank you very much for your attention.